In this video, we're going to continue with our study of differential equations and talk about higher order linear differential equations. In particular, if we want to solve an initial value problem of an nth order linear differential equation, that initial value problem has this form. The top equation there is our nth order linear differential equation, and the bottom line is the n initial values that we must have in order to solve the initial value problem. Notice that we use the same t value for our independent variable or our input value, and we use that for each of our initial values. We do have an existence and uniqueness theorem here for such a initial value problem, and that says that for any interval I which contains the t naught such that a sub n of t all the way through a sub 0 of t, g of t, and 1 over a sub n of t, if all of those are continuous on the interval I, then the initial value problem has a unique solution on that interval. If theorem 1 is not satisfied, then we say the answer is inconclusive, i.e. that theorem tells us nothing about the problem. Okay. So we want to look at an example here, and we're going to determine whether the existence and uniqueness theorem guarantees a unique solution to the following initial value problems. If yes, we're going to determine what the longest interval on which the given initial value problem has a unique solution. To solve this, let's notice that instead of solving 4 different problems here, this is actually the same higher order linear differential equation for each of these. So really, we're just going to work one set of problems, and that's going to be able to solve all of these 4 problems for us at once. So we'd like to first notice what our a sub n's are. So we notice that this is a second order linear differential equation. So our a sub 2, which is the equation on the far left, a sub 2 of t is t squared minus 1. Our a sub 1 of t is negative 2t, or sorry, negative 2t, yes. Our a naught of t is 2. Our g of t is 1 over t, and 1 over a sub n of t, which is a sub 2 of t, is 1 over t squared minus 1. Now, we want to find the intervals for which all of these are continuous at the same time. Notice that here we cannot have t is equal to 0, and this one implies that t cannot be 1 or negative 1. So in fact, our intervals here are from negative infinity to negative 1, negative 1 to 0, 0 to 1, and 1 to infinity. Now, the question asks, for the given initial value or initial t naught, what intervals can we guarantee that we have a unique solution? If we look at this first one, this says our t is negative 1. And notice that we don't have an interval in which negative 1 lies. Both of these imply that negative 1 is not in the interval. So for part A, we have that our answer is inconclusive. For part B, we look at the initial value, and our t naught there is 2. So we find the largest interval that contains 2 and has and is continuous for all of these functions, these coefficient functions that we had found. And the interval that is continuous for all those functions and contains 2 is 1 to infinity. So we have a unique solution on 1 to infinity. For part C, our T naught was -1/2. That lies in this interval from -1 to 0. So we guarantee a unique solution on that interval, and that is the largest interval on which we can guarantee that unique solution. And then finally, for part D, our T naught is -2. So this lies in the interval -infinity to -1. And that is our solution to this problem. All right. We're going to move on and do one more example in this video. But before we do that, we want to discuss something called homogeneous equations. So an nth order linear differential equation of this form is said to be homogeneous. And what is the difference here? The only difference is that our g of t is equal to 0. So we've used homogeneous previously in this course, but now when we talk about an nth order linear differential equation, homogeneous in particular means that our g of t, so that function over on the right, is 0. Okay? Everything else here, so this left side looks just like the nth order linear differential equation that we had stated in the previous page. Okay. And it turns out, by this theorem too, if we have k solutions to a homogeneous nth order linear differential equation, then a linear combination of those k solutions with ci through c sub k being arbitrary constants. So these are constant values, not functions of t, but just constant values. So if we have a linear combination of those k values, then this new value x is also a solution to the differential equation. In other words, if we find two functions that are solutions, then their sum will be a solution. Or if we find a single solution, then a scalar multiple of that function is also a solution. Moreover, every homogeneous linear differential equation always has the trivial solution x equals 0, right? If we plug in x equals 0 here, this term goes to 0, but the derivative of 0 is 0, so this term will also go to 0, and so on. So all of those terms go to 0, and certainly if we sum that up, we get 0. So we'll do a quick example here. And that is to find 5 solutions for the homogeneous linear differential equation x double prime minus x is equal to 0. Well, first off, one easy solution is that x of t is equal to 0 is certainly a solution. And now we want to consider, when does x double prime equal x? Do we have any functions that we know off the top of our head, in which case, at which point this is true? Well, you might recall that if we have x of t equal to e to the t, then certainly this is equal to the derivative of x of t and also the second derivative of x of t. So this is another solution. So we have a second solution here. We might also recall that x of t is equal to negative e to the t. Will give us a solution. Excuse me, that's not what I meant to write. E to the negative t will also give us a solution. If we take the first derivative, we get negative e to the negative t. But if we take the second derivative, that negative will end up canceling and we get back to e to the negative t. All right. And then, so we have those, but we also notice that if we sum them, so we could have x of t equal to e to the t plus e to the negative t. So if we add those two, we can also get a solution. And we can also get a solution by just multiplying by 5 or 2 or whatever you wish, any constant there. And really, we could even make more solutions. We have infinitely many solutions. Our general solution to this problem will end up being c1 e to the t plus c2 e to the negative t. So any solution of this form will be a solution to this linear differential equation, x double prime minus x is equal to 0. All right, that's going to end this first video. We'll continue on with more discussions on this topic in the next video.